Alright, so until this point we have been calculating scenarios where we have had bending stress and normal stress separately. But in many cases, we have actually both of those loads applied to our structure at the same time. And in those cases, we need to have a way how we can calculate the effect of the bending stress and normal stress together. Well, luckily, the way how we can do the calculation is very simple. It's just purely that we count those two loads together. Here we're going to calculate an example. So we have this cross section. It's T-shaped. It has a cross section area of 5,000 square millimeters. The second moment of inertia is 120, 10 to power 6 Newton millimeters, millimeter power to 4. Sorry. And the internal loads applied affecting on that structure are bending moment of 35 kilonewton meters and a normal load of 50 kilonewtons. Important thing to pay attention with these calculations is that the internal loads must always be located at the neutral axis of the profile, and you will see later on why that is the case. So let's calculate this example. So we're going to calculate the effect of bending, internal bending load and internal normal load separately. And let's start from the bending load. So we're going to calculate the bending stress for this profile. We remember that the bending stress is calculated with this formula in here, where the bending moment is divided by the second moment of inertia and then multiplied by the distance from the neutral axis to the location where we want to calculate the stress. Let's start by calculating the stress at the bottom of the profile down here. The distance from the neutral axis to the bottom of the profile is 100 millimeters to the positive Z direction, and therefore the stress at the bottom of the profile will be 29.2 megapascals, and the sign of the stress is positive, which means that the stress is tensile. A very important thing, which I have said multiple times, is that you always must use newtons and millimeters as a units in these calculations, and that way the results will be straight away in megapascals. And the same thing is in here. Now we have calculated the stress at the bottom, and now we can calculate the stress at the top. Well, at the top the stress is calculated with the same formula, but the biggest and the main difference in here is the fact that in this scenario the distance from neutral axis is to negative Z direction, and the distance is 50 millimeters, which means that the stress at the top of the profile is minus 14.6 megapascals. This means that the stress at the top of the profile is compressive. Now that we have calculated the bending stress on this profile, we can draw the bending stress diagram. It is linear as shown in here, and now we can calculate the normal stress. So the normal stress is calculated with this very basic formula that we already know. Normal force divided by the cross-section area. That will give us the stress. And quite simply, in this case, the normal load was 50 kilonewtons, and we divide that by the cross-section area, which was 5,000 square millimeters. And notice once again that the kilonewtons has been converted to newtons. And when we calculate this, we get that the normal load, normal stress on this profile is 10 megapascals. Well, like I said, when we want to calculate the combined effect of normal stress and bending stress, what we do is that we just simply calculate those two things together. So the combined stress, the total stress, will be the bending stress plus normal stress. Here you can see one more time the formulas which are used to calculate both of these. And since we have already calculated for both of these cases separately, we can just simply sum these two things together. At the bottom of this profile, the bending stress was tensile, positive value, and also the normal stress was tensile, positive value, which means that the total tensile stress at the bottom of the profile is 39.2 megapascals. At the top, however, the bending stress was negative, minus 14.6, and the normal stress was tensile, 10 megapascals. So when we calculate these two things together, the total stress at the top of the profile is still compressive, but only minus 4.6. And now finally we can just simply draw the stress diagram over this profile, and it will be linear, just like here with the pure bending, but it will be shifted to the direction of the normal stress. So that's how you calculate the compound effect of normal stress and bending stress on a structure.